Hi, welcome back to Mechanics and Control of Robotic Manipulator. Last class we gave introduction to motion control and types. So this particular class we would be starting with kinematic control as one of the type which we have seen in the last lecture. So here we start with what you call inverse differential kinematics, then we will talk about kinematic control. Even this kinematic control can be done in either joint space or task space. So here we are not talking about sensory space because we are not going to work on real time system in this particular lecture or the course. So that's why we have restricted only joint space and task space. So let us move to the inverse differential kinematics straight away. So what is inverse differential kinematics, which we can consider as a feed forward control, or we can say it's a open loop control. So where we are actually we end up with the joint space. So in that case, so what we are trying to see, so the position trajectory is given. So in the sense we have to follow that position trajectory tracking. So what additional constraints would be given? So the q desired and q desired dot would be given to us. Okay. So further, so either this would be given if it is a joint space, if it is a task space, the mu desired and mu desired dot would be given. So in the sense end effector position and velocity would be given. So what we expected the q of, you can say, t tends to q desired, but that is not directly guaranteed. But what we can actually ensure, if the q of t is equal, q dot of t is equal to q dot of desired. So that is what we are trying to see. So in the sense available is, you can say, Jacobian matrix, because this Jacobian matrix is required when we try to do, you can say, end effector position trajectory tracking. So then you can see what we need to find out. We need to find out the q dot. Since it is actually inverse differential kinematics, we say that the q dot is nothing but, you can say, q desired dot. Okay. So if it is actually like this, so the j inverse of q into, you can say, mu desired dot. So that would be q dot. So this is what we are calling as a inverse differential kinematics. So for that there are some conditions. So that conditions I am trying to put it here. So what conditions? So the objective here to follow the given position trajectory. However, what assumption explicitly given? So with an assumption that the initial values of the actual and the desired states are equal, in the sense, so q of 0 and q desired of 0 are same. That is what we are actually written it. So further what happened, it should have non-zero, you can say, desired velocity, then only the differential kinematics will work, right. So if that is the case, so if it is in the task space, you can say the mu desired dot supposed to be non-zero and mu desired at t equal to 0 and mu at t equal to 0 both supposed to be equal. So if that is the case, what we can do, the control law, we can directly write q dot as q desired dot, or so q dot can be written as j inverse of mu desired dot. So this is what you call inverse differential kinematics. This we have seen already in the regular lecture. So here we will see in a, you can say, block diagram base. So the robotic system will give as per a kinematic level. So it would be give as a q output, and what would be the input? So q dot, right. So this is what we assume. And the inverse differential kinematic means what happened. So there would be a trajectory planner. This trajectory planner will give what? So we assume that it is actually end effector. So end effector position and trajectory. So then what happened? This would be giving mu desired dot and mu desired. So these two would be available from the trajectory planner, but you need q dot. So for that what we can use? So you know that mu dot is actually j of q into q dot. So in the sense q dot can be written as j inverse of, so q into, sorry, so this one is actually mu dot, but here we are thinking about desired. So this desired means this is also desired. So then what we can actually do it? So we can bring one Jacobian inverse. Okay. So then you multiply with this, that would be equal to q dot. So that is what we are bringing it. So now there are two ways we can do it. So we can do the, you can say, inverse kinematics. Okay. So then we can actually do it here. Okay. So this way we can actually do it. So the q desired can be fed. So then this would be Q desired, or we can take the Q as the feedback and we can directly as a J of Q. So either way we can do. So more commonly when we try for you can say real time system, the Q is easily obtainable, then we can consider as a feedback. But if you think about strictly, so we have to do this, but we are actually like more commonly using in this aspect. Okay, so where we assume Q is actually like known to us, in the sense J of Q inverse is exists to us. Okay, I already told strictly we can write this way. So J of Q desired inverse into so mu desired dot. Okay, so this is the equation. So for that we have to have so the inverse kinematics that will give so the Q desired, right. So Q desired will give. So that is what we supposed to take as a feedback, but more commonly the robotic community people, so they take it Q and then correct it the J. Okay, so either way we can do it. The state inverse differential kinematics means this, but you can actually like use it either way around. So I have used this one more commonly, which was used in the book. So that's what I have written it here. Okay. So now we will actually like move to the kinematic level control, where the joint space is the consideration. So then what happened? The desired would be joint position and joint velocity, which is nothing but Q desired and Q desired dot. Okay. So if it is a set point control, the Q desired dot would become 0. Okay. So then what one can actually like thought about it. So we can actually like see what are the things supposed to be available. If we think about a kinematic or motion level control, the Q of T, which is nothing but the actual joint position, supposed to be available. Further, so if we are actually like moving the spaces, so we may require Jacobian, but if we talk about joint space, this may not be directly required. Okay. So then what we are trying to find out? We are trying to find out what would be your actuator speed. Okay. So in the sense joint velocity should be known. So for that what we are actually like trying to use, we are trying to say that some objective where Q desired minus Q, as I call Q tilde, this Q tilde supposed to go to 0 when T tends to infinity. So this is what my objective. If I assume this is the objective, so what I can choose? So Q tilde I can choose something like exponential, some positive constant with the T. If I assume a scalar, I can take as a lambda, otherwise I have to take lambda as a matrix with you can say diagonal value, but right now I assume that this is the case. So then what one can actually like feel it, so you can actually like do it this in a simple aspect. So for that what we are saying that it is exponentially stable. When T tends to infinity, the Q tends to Q desired. So in the sense Q tilde is supposed to go to 0. So what we define, so the Q tilde we defined in this way. So where Q tilde I am defining as Q desired minus Q. So that this can be incorporated, provided the lambda should be a positive constant. So now in that case, so we take this and we differentiate it. So what it will come? So Q tilde dot equal to minus lambda into E exponential of minus lambda T. But what is this? This is nothing but Q tilde, right? So now we can actually like substitute that. So then I rewrite. So what happened? Q tilde dot plus lambda Q tilde equal to 0. It's a simple first order system where the lambda is a positive constant. So then the error dynamics is actually like stable, right? It is actually like tends to 0. So that is what we are trying to do. So now the Q tilde dot I can write as Q desired dot minus Q dot. So then the Q dot is actually like required, I can rewrite. So that is what I am actually like writing it here. So now in that case the Q dot I can write it as this. So this is what my control law. Okay. So this is the control scheme, I can say. This is a kinematic control scheme. So this is actually like a feed, so the forward term, and this is actually like a feed back term. Okay. So in that case even the Q desired dot is 0 or you don't know, still this control will try to cope up and go further. Okay. So in order to understand that, what we assume that this is not known, and we try to do a simple proportional control. So that is what the next idea. Before that, we will actually like see the same thing in a block diagram base. So where the robotic system will give these two. Okay. So this is the output and this is the input. So now we are actually like trying to see what would be the trajectory planner will give, since it's in a joint space. So it will give q desired dot and q dot desired and q desired. So these all actually like input, and I take this and calculate the error and multiply with, you can say, lambda. So then I can actually like add it this, right. So that is what I am trying to do. So now I calculated the error, this is nothing but q tilde. So then I can actually like feed it that to some block. So where I said q desired dot plus lambda q tilde would be the q dot as the input, right. So this is what we have seen in the previous. So this is what we can say the kinematic control, you can say, model. The same thing can be modified for the task space, but before going to see the task space, we can see how we can actually like expose to a simple feedback with a without actually like even feed forward. So for that we assume the initial thing all are actually like same, only thing the q desired dot is actually like not available to us. Okay. So then what one can do, we can simply calculate the, you can say, error, and we can actually like make it a simple proportional constant. Then we can consider this as the control law. This will work. Sometime what happened, this q desired dot is not there. So what happened, this would actually like give some kind of steady state error. In order to avoid the steady state error, so what people try to do it, so the q tilde go to a second order dynamics in an integral level. So then we will bring the proportional and integral control. So then that can be overcome. So this is what we can say. So this may end up with some steady state error as long there is a q desired dot is some value. Okay. So non-zero, then this may end up with a steady state error. So in order to overcome that, so people come up with the proportional and integral control. So then you can see like this is the way we can actually like write it. So then you can see that the q dot can be written as a proportional control and integral control, right. So further it provides that both control gains are actually like positive. So that is what you need to know. Since it is actually like q is a vector, so then this matrix supposed to be actually like positive definite matrix. More or less like people try to use this Kp is actually like positive. In addition to that, this is actually like symmetric. So this is actually like further extended, but most of the you can say robotic researcher that to like when apply in real time, so they take it this actually like in a diagonal value. Okay. So positive values in the diagonal only, so off diagonal all are 0. So that way they take it, say either Kp or Ki, this is also one standard. So some people even used to the other way around. So Kp take as a simple some scalar value into identity matrix. So this is also possible. So this lambda is a positive constant, provided this is a positive constant, then this control will work very well. But the steady state error may vary based on the lambda choice or based on the positive definite matrix. Okay. So this is what we can see as the kinematic level control. We will go to the kinematic level, but in task space. So for the task space, what we can see, this overcome the steady state error. For the task space, what would be given? So instead of desired joint position, it would be given desired end effector position, desired end effector velocity, and if it is a set point, the desired end effector velocity would be 0. Then what we are actually like expected, it would be available. So the actual end effector position and so actual joint position, because sometimes the inverse kinematics is not possible straight away. So then people actually like try to use the actual joint position. So in that case, what one can see, so the Jacobian matrix is necessary here. So Jacobian and Jacobian inverse also exists, because this supposed to be exists in the sense. So this determinant is non-zero, or if it is actually like rectangular, then we have to say this j plus of q is exists. Okay, in the sense pseudo inverse supposed to exist. So then what we can see, what we need to find out, the same thing, we need to find out the q dot of t, right. So how we can find the q dot of t? The same principle we will use. The objective here is actually like the mu tilde supposed to tends to 0 when t tends to infinity, okay. So or the other way around, the mu tends to mu desired when t tends to infinity. So if you apply the mu tilde, I can write it as so exponential of minus gamma into t, where the gamma is positive constant, and again mu tilde I have defined as mu desired minus mu. So based on this I can write this equation, okay. So then this is actually like known, and this is the equation which we will be obtaining based on that. So then we can actually like provided put the gamma is actually like positive, then we can get this. So from there mu dot we can substitute as, so this relation we can substitute, then we can find the q dot in this way. So now this is the control law, so which is for the task space level. So I have actually like make it the same thing in block diagram base. So only there was a small error, I will correct it in you can see the handout. So the robotic system will give the output as q and input is q dot. So then we can see the trajectory planner. The trajectory planner will give the mu desired dot and mu desired. So now we need mu, right. So the mu we have to do it in a forward kinematics, okay. So this I have written as actually like inverse. So this is supposed to be written as forward kinematics. Please correct it. I will correct it in the handout. So once you know this forward kinematics, okay, so you can see that the mu would be obtained. So then you can actually like calculate the mu tilde. So once you calculate the mu tilde and mu desired dot is known, so what we can do, we can make Jacobian inverse into, so mu desired dot plus gamma into mu tilde. That is what we are trying to do. So this is, so what we actually like use it. So what one addition, so you need this q because this j of q is required. Some people here again they use the, you can say from here the inverse kinematics and then this desired, but I prefer this is a feedback, so better we can use q, so then we can actually like make it. So that is what the whole idea. So now I hope you are actually clear. So what is actually like a kinematic control, and what all about you can say it a task space scheme and joint space scheme, and in the next lecture we will see some numerical example along with MATLAB simulation, so that you would be getting more clarity on this kinematic control. Once that is clear to us, then we will move to dynamic control. Until then, see you, bye, take care.